Hello everyone, welcome to another control system class on system simplification. In previous class, we have seen what block diagram reduction was. In today's class, we are going to see another method for your system simplification called as a signal flow graph method. So in signal flow graph method, your control system is represented using nodes and branches. So the node points are the points between the branches, and the branches are the connecting lines between the nodes as shown here in your diagram. So the signal flow graphs can be obtained or can be drawn for any given system from the block diagram, and then they can be simplified. So the logic is, or the notion is, that the signal flow graph simplification is much simpler, and the idea for signal flow graphs come from your electrical circuit network analysis, and it's like it's like much simpler than block diagram reduction. So what we do is we convert your block diagram system into a signal flow graph, you simplify it, and then you go back, you take a simplified signal flow graph, translate into a block diagram, and then you go for the infrastructure design and prototyping of the system. So this is the idea and use for using signal flow graph, the main purpose for introducing this in your class. So let us see how do we simplify. So we have the same set of rule sets we have seen for block diagram. The first two are the same. X1 is equal to, sorry, it should be X2 is equal to AX1 and X3 is equal to A1X1 plus A2X2, which are very obvious from the given figure. And then you have the multiplier, so you can simplify it with two branches A and B into a single branch AB, which is shown in your third rule set. Now, the signal flow graphs or even any other simplification step is aimed at converting your complex system into a simpler system, and also into finding the transfer function of your system. Right, so in order to find the transfer function of your system using the signal flow graph method, we have something called as your Mason gain formula. So your Mason gain formula is nothing but a formula that operates on your signal flow graph, and we're going to see how in this class. But to summarize it as a formula, you can write my Mason gain as your 1 by delta. I call that triangle symbol as delta here, sigma k, which is my summation, pk delta k. So this is the formula for Mason gain, and when I'm talking about Mason gain, it is the equivalent of transfer function. So finding the Mason gain for a signal flow graph, that is the same as saying find the transfer function of the signal flow graph. Good. So what do these notations mean? What do these delta, pk, and delta k mean in your Mason gain formula? So the pk is your forward path gain of the kth forward path, right? So it means that you are finding the forward path in your signal flow graph and computing the gain. So how do we do that, and what is the meaning of forward path will be clear in the next slide when we do a numerical on this. So the delta k is the same. The delta k is for delta for non-touching, and you have the delta. So the delta k is derivative of delta. So I have not written the full expression for delta k, but I have the full expression for my delta, which is given by 1 minus sum of individual loop gains plus sum of gain products of loop pairs of non-touching loops minus 3 non-touching loops, gain product of 3 non-touching loops. So we will see what do these notations mean in a real example when we solve a numerical, and we will find what is the pk, delta k, and delta for a signal flow graph, and it will be clear for you how these are computed and how your system simplification using signal flow graph happens. Good. So we have the numerical here. The question is find the overall transfer function for the given signal flow graph. And for the signal flow graph, the transfer function is nothing but your Mason gain. So here, okay, so it's given as Mason gain formula, so we can use it. So there's no other way to find the transfer function except the Mason gain formula. At least in this course, we are only seeing that method, which is useful for measuring your transfer function. Good. So in this given question, you have to find all those terms like delta, pk, and delta of k. So we are going to do that and substitute in your Mason gain equation, and that is going to give you the transfer function of this system. So we are numbering the nodes 1 to 8. So there are 8 nodes in the system. And then what else we have? Do we have the gain between the nodes? Yes. So yeah, okay. So you have kind of what are the loops? You have forward paths, you have loops. So we will see what are those in few more steps. So I'm just drawing the question here, and okay, the gains are coming now. So I have a negative gain of H2, negative gain of H3. So whatever is written over the branch, we call it as the gain of that branch. Or in a system, it is the gain between the nodes 6 and 7, right? So that is what, okay, between 1 and 2, you have a unity gain 1. And what do we have between Okay, I think I'm getting this wrong. Yeah, no, I just want to use a different color for highlighting the gains. Good. That's a good thing. So it's more clearer for you. So between 1 and 2, I'm seeing a unity gain. Between 2 and 3, I have my G1. Between 3 and 4, G2, 4 and 5, G3. Good. So these are all the gains, and these are what is given in your question. So now let's see the solution for these type of problems. So how do we find, or what do we do first? How do we get started with this? We look at the forward path. So let us see what are the forward paths given in this system. So if you look at this system, or if you look at the signal flow graph representation, we need to find, and what is the definition of a forward path is a path containing all the arrows from left to right. So if you see here, you need to see which is containing all the arrows from the beginning node to the end node, and we are looking at 1, 2, 3, 4, 5, 6, 7, 8. Good. So if I take that path and see, I'm getting all forward arrows, and my second forward path is 1, 2, 5, 6, 7, 8. So that is also correct. Right. So I'm just going to represent the forward paths from my question here. So this is the first forward path. I have highlighted it for you, and now I am highlighting the second forward path here. As you can see from the start node, from the beginning 1 to 8, it is all unidirectional. Arrows are all in forward direction. So now we have the forward path, that is the first step, and these forward paths are used in the gain of the forward path is my pk in my Mason gain formula. So the Mason gain formula, I have pk, and in this case pk, the key value is going to be 2 because we are having two forward paths. So which means my p1 and p2 are going to be the gains shown here. So my P1 will be the first forward path gain, which is G1, G2, G3, G4, G5, and my P2 is going to be G4, G5, and G6. Excellent. So which means if I have two forward paths, I am going to have two delta, right? So delta K is also going to be delta 1 and delta 2, so we need to find those also. So we have just found a single variable in the Mason gain formula. Now next, let's go for the delta. So the delta formula is 1 minus what? 1 minus the sum of individual loop gains plus the sum of non-touching loop pairs, right? So this was the formula for delta. So let us now, let us find those loop gains in this step. So what is a loop? So before I start you with the loop gain, what do you mean by a loop? A loop is nothing but something that has the same starting and ending node. So which begins at a node and ends at the same node, that is what we call as a loop. As can be seen here, your loops are AB and ABC. Now let's identify the loops in your question since we are interested in finding the individual loop gain. So my loops here I have is my 3, 4, 5, yes. And then I have my 3, 4, and then I have my 6, 7. So I have 3 loops in this question, and my loop gains are nothing but the product of the gains of their branches. So which means my 3 to 4 gain is going to be just G2 into minus H1. So just multiply those gains. So I'm drawing the individual loops, and I'm going to show you how to find the individual loop gains here so that it is clear for you. The first loop gain is given nothing, just minus G2 H1. Just take the product And if your values are not given in the question, just assume it to be 1, right? So if the gain or if the variable is not expressed in between branches, that is supposed to be 1, and you have to assume it as 1 and carry on with your computation for transfer function. So for the loop 3 and between 6 and 7, and that's going to be my minus G5H3. So this is one of the components in determining the value of delta, which is 1 minus the sum of your individual loop gains. So that is given here and that is calculated well. Now from this we need to find the next is the loop pairs. So we are going to group these loops as touching loops and non-touching loops. We will see that in a bit. So I have written here the Lebo loops contain touching and non-touching. So what it means to be a touching loop and a non-touching loop, we are going to see here. So loops are said to be touching with each other when they share a common node. So in your case of example 3, 4 and 3, 4, 5, you have the common nodes between these two loops as 3 and 4. So which means these two are your touching loops. And for non-touching loop, it is the opposite case. Both the loops don't share any nodes in common, which is the case with 3, 4 and 6, 7, 3, 4, 5 and 6, 7. Good. So if you see these two pairs, if you see 3, 4 and 6, 7, 3, 4, 5 and 6, 7, then that is your non-touching loop. Excellent. So now the next part of my delta calculation is we have to find the product gain, right? We have to take the product gain of your non-touching loop and sum it up. So here we have what are the loop pairs that are non-touching. We have 2, 3, 4 and 6, 7. So their product gain is nothing but the individual gain of 3, 4 into multiplied by the individual gain of 6, 7. So that is my gain of loop pair 1 shown as G2, G5, H1 and H3. The same thing is applied for my next loop between 3, 4, 5 and 6, 7. Good. So that is my another term for the calculation of my delta. And here I don't have 3 non-touching loops, which was the next step, next thing to see. If I had 3 loops and all 3 loops did not share any common nodes, then I have my 3 non-touching loops. But that level question we are not doing here. I think now we have everything to compute our nascent gain, which would in turn give our transfer function. So my delta is calculated as 1 minus the loop gain sum plus the loop gain 2 sum. So when I say the loop gain 1 sum, they are the first stage, that is the individual loop gain, right? So I can say they are the single loop, and it is in this case we are not bothered about overlap and non-overlap. We are not pairing them. And plus the loop gain second was the no overlap pairs. So my first component had loops 3, 4, 3, 4, 5 and 6, 7, and my second had the gains of 3, 4 and 6, 7 plus the gain of 3, 4, 5 and 6, 7. So together this is going to be given as 1 minus. So I'm just going to write and just substitute the values that we have calculated till now, and that is going to give you your delta. Excellent. So we have now we have computed our pk and we have computed our delta. So we are still left with the delta k. Excellent, right? So what is your delta k? How do we find delta k? Right, so that we will see now. So I'll write my pk also, which is my p1 and p2, and delta of k has something to do with all these things we have done up till now. So let us see that in a bit. So my P1 is this is equal to the gain G1, G2, G4, 5, and P2 is going to be equal to G2, G4, G5, G6. Good. So that is my P1 and that is your P2. Now let's come to our delta K, and the rule set for finding your delta K is delta K is computed as 1 minus the gain of loop not touching with the forward path. Yes. So it is the sum of the gains. So it can be 1 minus the sum of the gains not touching your forward path. So in this case, if you see, the forward path 1 is highlighted here, and all the loops are touching your forward path. Good. So all the loops are touching your forward path. So that is shown here. And next, if you take your second path, then what happens is, if you take your second path, then for your second path, you have one, you get, for your second path, your 3, 4 is not touching the forward path because the 3, 4, 5 still share a common mode of 5 with your second path. So here, this is not touching with your forward path, and that gain is going to be is equal to 1 minus gain of the forward path, or delta 2 is equal to 1 plus 0. So if you had here more than one loop, then your gain is computed as the sum of the gains, right? So gain of, if you have two loops, you take the gain of one plus the gain of other, and 1 minus that is going to be your delta gain. So the Mason gain formula for the transfer function C of S by R of S is given by this, and now we have your P1, P2, delta 1, delta 2, and 1 by delta, and substituting all this into these expressions, all the values into the expressions, we get our transfer function. Good. So that is how you solve a problem on signal flow graph and the reduction of signal flow graph using certain rule sets. So here basically we are following the Mason gain simplification, right? So that when you when you apply the Mason gain formula to the signal flow graph, you are simplifying it. And this simplification is considered better, much better than your block diagram simplification, because this is less error prone and there should be less mistake because everything is predefined and everything is very systematic, right? In block diagram, it's like up to the user whether you move the block to the right or you move the block to the left. It is depending on the user. So it can vary. The simplification steps can very much vary, and there is no set, like there is no order of rules. Even though we are keeping the overlap as the first rule, so signal flow graphs are much um, much accurate, and they are very less prone to multi-user error. So when multiple users are simplifying the same signal flow graph, all will end up getting the same output. So now what we have here is, I want to show you, I told you, right, a block diagram can be converted into a signal flow graph and it can be simplified. And then once you have the simplified one, you can go for the infrastructure development or prototyping of it. So that is what I would like to show you here. So you have a block diagram given in the question, and you want to convert that block diagram into a signal flow graph.